Hi, this is Tzvi Rosen with another lecture in our series on the history of calculus. In this lecture, we'll discuss ancient Babylonia, their mathematics, and the ways in which they anticipated the calculus with their approximation of square roots. So first, a brief word on Babylonia. This is an empire situated in the Middle East, sitting on the Persian Gulf, in the region called Mesopotamia between the Tigris and Euphrates rivers. It existed in various forms over a very long stretch of time, 1894 before the Common Era to up to 224 in the Common Era. But we're going to be focusing on the first Babylonian Empire. This is also sometimes called Old Babylonia, or OB. This was focused in 1894 to 1595 BCE. The most notable emperor in this period was Hammurabi. He was known for the legal code of Hammurabi, one of the first and most expansive legal codes extant from the ancient world. The image on the right is an image of Hammurabi presenting this law code to his deity. And this is found on a stele, which is a large stone object on which the code of Hammurabi is carved, which is stored in the Louvre in France. Another notable thing about Babylonian civilization is they wrote cuneiform, which are wedge-shaped markings on clay tablets, and that's how they recorded information. Okay, now about Babylonian mathematics. They had a base 60 called sexagesimal number system, and this has stuck around in a lot of ways. For example, 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle, so a multiple of 60. And just to practice looking at what that might mean, so if we take the date 9/4/24 and we interpret this as a base 60 number, we would associate a power of 60 to each of these numbers. So we would take 9 times 60 squared plus 4 times 60 to the 1 plus 24 times 60 to the 0. Then we would compute those products and add them up to translate this into base 10. It would be 32,664. So one issue with the way that Babylonians wrote down numbers is that they didn't have a way to specify where the decimal point was. So maybe they meant 32,664, or maybe 9 was meant to be associated with 60 to the 0, and then 4 and 24 were supposed to be fractions. So we would say 9 times 60 to the 0 plus 4 times 60 to the minus 1 plus 24 times 60 to the minus 2 would add up to 9 and 11 150ths. Okay, so this ambiguity is something that later societies would solve by having a decimal point or some other radix. Other mathematical things the Babylonians were doing were using the Pythagorean theorem to compute lengths and solving some quadratic equations by completing the square. They didn't formalize this as equations. They didn't have the notation of variables to solve and things like that. But they were able to solve geometry problems that were equivalent to quadratics. Here is an ancient clay tablet that has given evidence to the idea that the Babylonians knew how to compute square roots to high accuracy. So you can see on the left is a high-quality picture, and on the right is a cartoon, so you can see the imprints a bit more clearly. Hopefully you can tell that this is an accurate representation. And we can interpret each of these sideways wedges as tens. So this number would be represented as 30, whereas the vertical wedges are 1. Okay, so this would be 1. This would be, so 2 tens and 4 would be 24. This is 5 tens and 1, so that's 51. And then we have 1 10, so that gives us 10. Okay, now down here we have 4 tenths and 2, that's 42. 2 tenths and 5, that's 25. And 3 tenths and 1, 2, 3, 4, 5 is 35. Okay, so let's put some semicolons there to distinguish between these. So, okay, great. So we have for seven places, 7 digits, I guess, in a base 60 system, as well as this 30 up here. So that's 8 numbers. So how does this tell us anything about square roots? And what is this square in the background? Well, let's interpret these numbers. So we have, again, 1, 24, 51, 10, 42, 25, 35. So the top line is pretty clear how to interpret. If you compute this base 60 expansion, you get something like 1.41421 and then repeating 296. As for the square root of 2, that's 1.414213. So we get a correct estimate for square root of 2 up to 7 digits, which is pretty good considering how far back we're going in time. How about the second line? Well, again, so here we have a radix issue. So if we start at 60 to the minus 1, then do this computation. So it would be 42 over 60 plus 25 over 3,600 plus 35 over 216,000. Computing that, we would end up with 0.70710 and then 6481 repeating. And that is quite close to the reciprocal of square root of 2. It's not immediately obvious. So looking back at this picture, it was not immediately obvious why someone would write down square root of 2 and its reciprocal on this sheet. So I like this alternative explanation, is that instead of starting at 60 inverse, at 60 to the minus 1, we start at 60 to the 1. And then what we're looking at here is 42.42638 bar. This number is approximately equal to 30 times the square root of 2. Because we're looking at, and this is approximately 42.42641, etc. Okay, so that gets pretty close. So why would we need 30 times the square root of 2? Well, then let's look at this picture again. This might be a geometry student who's trying to compute the length of a diagonal of a square of side length 30. Okay, so that would be this side length, and then this number. So maybe the student would write down square root of 2 to high accuracy to make sure that they're getting to start off their computation, and then this number is the length of the diagonal, 30 times the square root of 2. Okay, so that would be this length. Okay, and then a natural question is, how is it possible that 1 over the square root of 2 and 30 times the square root of 2 would be so similar that you could mistake one for the other? Well, it's a simple consequence of this base 60 system, right? If you have 42 times, so if we take 1 over square root of 2 in our original formulation, and then we shift everything up by a factor of 60, well, 60 is 2 times 30, so the 2 cancels with the square root of 2 to leave square root of 2, and that explains why shifting, which is the same as multiplication by 60, gives us the value of 30 root 2 instead of square root of a half. Okay? So this tells us that they knew the square root of 2 to very high accuracy. And the question then is, how would they have done this? And various historians have hypothesized about this, and the current most popular explanation is that they had Heron's method. So Heron was a Greek mathematician. So he was a Greek mathematician, and he published or was known for a result for an approach to computing square roots, which goes as follows. So let's say you're trying to compute the square root of a number n, which is bigger than 1. If it's not bigger than 1, you can do its reciprocal. And you want to take a first guess, x0, which you think is close to the square root of n. And you also want an accuracy epsilon. Okay, so this is an iterative algorithm. You repeat it until you have the desired accuracy. And so we need to set that threshold to start. Okay, so once you do this method, your output will be a value y such that y, the error, absolute value of y minus the true square root of n, is bounded above by epsilon. Okay, so this should happen greater than or equal to. Not likely to be an issue, but still. Okay, so first you set x to be your first guess, and you compute an error, which is the error of your first guess. And for error, we approximate the true error. Since we don't know the square root of n, we can't actually compute how far we are from it. Instead, we approximate this as half the distance of the square of your guess from n. Okay, so this is an approximation, and you can show that this is quite close in general. This is an approximation to the true error. It's an upper bound. Okay, meaning if you know that the error computed, this approximation of the error is less than epsilon, then the true error will be even less than that. Okay, so while our error is greater than or equal to epsilon, we are going to iterate, and our new guess will be the current guess plus n divided by the current guess. Okay, and then you just replace your guess with your new guess, and you recompute the error. Okay, and if your error is still too big, then you do this again. Okay, and when you finish, when your error is small enough, it's below the accuracy that you require, then you return your guess. Okay, let's see an example of this. So let's say we want to compute the square root of 2. So we always need a guess, a first guess, and then a desired level of accuracy. So we're going to guess 3/2, right? We know the square root of 2 is bigger than 1. We know it's smaller than 2, so 3/2 is a good place to start. And we want accuracy 10 to the minus 6. Let's do the first iteration by hand. So we have square root of 2, so we're guessing 3/2. So our x new will be 1/2 times 3/2 plus 2 divided by 3/2. Okay, so let's simplify. This is 1/2 times 3/2 plus 4/3. That's the same as 1/2 times 9/6 plus 8/6. And that is equal to 17 over 6 times 1/2, so that's 17 over 12. Let's try to get a few decimal places in the expansion of 17/12. We have 17 divided by 12. And we'll take a few places here. So first, 17 goes into 12 once. Get a difference of 5. Into 50, 12 goes 4 times. Then we get 20. 12 goes in there once. Looking good on square root of 2 so far. We get 8 over here, 80. 12 goes in 6 times. And then we get 72, and we get 80 again. So we see here this is going to be a repeating 6. So our estimate in the first step, so our x0 guess is 3/2, which is 1.5. And our x1 guess is 17 over 12, which is 1.416 repeating. Already a lot closer, but obviously still not correct. And we would, and not within 10 to the minus 6 accuracy. So we would iterate. But as we can see, it's a lot of calculation to iterate. So fortunately, we have computers nowadays, though the Babylonians did not. And we can get this sequence of approximations. And already by the 4th approximation, we are at 10 to the minus 10 error, below 10 to the minus 10. So our accuracy is achieved already after 4 iterations of, or sorry, even 3 iterations, because the first one here is just our initial guess. x0, x1, x2, and x3. So this seems to converge quite nicely. We see that this iteration gets us very close quite quickly. But one thing I didn't justify earlier, I estimated our error by 1/2 of x squared minus n. And I just want to justify why that is. So if we have x squared minus n less than or equal to delta, my claim is that the absolute value of x minus root n will be less than or equal to delta over 2. Okay, and the argument goes that if x squared minus n is less than or equal to delta, well, this can be factored as a difference of squares. This is equivalent to saying x minus root n times x plus root n is less than or equal to delta. Okay, now we're going to have to divide by both sides by x plus root n. Okay, so this is equivalent to absolute value of x minus root n being less than or equal to delta over absolute value of x plus the square root of n. Okay, now a fraction is bounded above by something with a smaller denominator. Okay, so we know that x plus the square root of n, since x and n are both bigger than 1, or at least 1, this has to be at least 2. So this is going to be bounded above by delta over 2. And that's where this bound on our error comes from, so that we don't so that we can approximate the error from square root of n using the error from x squared minus n. Okay, and now we're going to prove that this algorithm actually converges, which is certainly non-trivial. It converged for us really nicely, but it's always a good idea to prove these things mathematically, though this, of course, is not something that the Babylonians themselves would have done. So to do this, we first prove a lemma that all estimates after our initial guess must be greater than the true value of the square root of n. Okay, so let's prove that. We're assuming that xk is greater than or equal to 1. And now we're going to show that xk plus 1 will be greater than square root of n, greater than or equal to square root of n, I should say. So what is x? So xk plus 1 is equal to 1/2 times xk plus n over xk, right? That's how we do this algorithm. And we want to show that this is greater than or equal to the square root of n. Well, we know that squaring is a monotonic function. So if we square this and we get something bigger than n, that tells us that we started out with something bigger than square root of n. So let's compute that. So we have xk plus 1 squared is 1/4 xk squared plus 2n. Okay, and that's because you're multiplying n over xk times 2 plus n squared over xk squared. Okay, and suppose we were to subtract n from this. So let's pull this over. And now we can subtract n. So this is going to be equal to 1/4, and pulling this minus n in, we're going to have to multiply it by 4, so we get xk squared plus 2n minus 4n, that gives us minus 2n, plus n squared over xk squared. Well, this is actually another square. This is the square of 1/2 times xk minus n over xk squared. And we know that any square of a real number is obviously positive, so that tells us that xk plus 1 squared is greater than n, or equal to, which tells us that xk plus 1 is greater than or equal to the square root of n. Okay? So any guesses we're making are going to be above the true value. Okay? And now we'll prove that the sequence of values converges to the true square root. And we're going to do that by talking about the error term. So we have ek will be the error xk minus n, minus the square root of n. Okay, and so we're going to try and formulate ek we're going to try to relate ek plus 1 to ek and show that the sequence of errors is constantly approaching 0, or is approaching 0 at a fast rate. So let's reformulate this to xk equals ek plus root n, and similarly xk plus 1 equals ek plus 1 plus root n. Okay, but we also have an expression that relates xk and xk plus 1, right? We know that xk plus 1 equals 1/2 xk plus n over xk. And replacing these, subbing in these values, we get ek plus 1 plus the square root of n is equal to 1/2 times ek plus root n plus n over ek plus root n. Okay? So subtracting root n on both sides, we get ek plus 1 is equal to 1/2 times ek minus root n plus n over ek plus root n. If we put all of this over a common denominator, this is 1/2 of, well, ek plus root n times ek minus root n is ek squared minus n, and then we have the plus n term all over ek plus root n. Okay, so let's grab this. take this to the next page. So we have now, just condense a bit, that we have this expression for our ek plus 1. We can cancel the ends to leave 1/2 ek squared divided by ek plus the square root of n. You can get an upper bound on this fraction by making the denominator as small as possible. So we can make, we know that ek plus root n has to be bigger than ek, so let's make it ek, and we're left with 1/2 ek. So what this tells us is that the error is halving at each step. Okay, so that means that we're going to get an error which is bounded above by 1/2 to the n. So this means that ek will be bounded above by e0 divided by 2 to the k, and we know this approaches 0 as k approaches infinity. Okay, so that tells us that this converges, but it also tells us it converges at a very fast rate because the error is halving at each step. So that's a very efficient algorithm. Some final thoughts on this. That we started our series in Greece, but even going further back, all the way to the first Babylonian Empire, they had this iterative method, most likely, for computing a square root, which tells us that they were describing sequences approaching limits as a way to compute desired values. No formal proofs are given, and still they get accurate results. In terms of why they were doing it, well, they were trying to do geometry problems, but they started from those geometry problems, and they moved into considerations that looked forward to the discovery of calculus. All right, in the next lecture, we'll talk about some summation formulas from the Islamic Golden Age. Thanks.